Geological archives hold the physical history of the Earth, but for decades, these massive collections have suffered from a critical operational flaw. The data is trapped in the rock, and the rock is trapped in a room. The Smithers Exploration Group, or SEG, holds a prime example, a collection of over 2,000 physical rock specimens representing the vast Cordilleran suites of Western Canada. When they began assembling this catalog in the 1980s, the goal was straightforward: capture the geologic heritage of northern British Columbia to train local geologists and prospectors. But physical collections demand physical presence. Because these specimens are geographically locked to a single facility in Smithers, the archive became chronically underutilized by the broader global mining industry. To solve this, SEG initiated a project to decouple the data from the physical stone, engineering a system to turn an isolated storage room into an active, globally accessible virtual field school. They built a three-part modernization pipeline: high-definition 3D digitization, non-destructive spectral analysis, and precise GIS spatial mapping. This hybrid approach removes the geographical barrier, allowing anyone in the world to analyze these specimens as if they were holding them in their own hands. The pipeline begins by migrating the physical archive into a standardized, searchable digital format. Every sample in the 2,000-piece collection was re-examined and tagged with precise metadata, categorizing plutonic, volcanic, sedimentary, and metamorphic suites, alongside specific stratigraphic data. This table is the foundation of their web-based catalog. It allows users to query the collection using a keyword search bar to filter by suite names and read detailed mineralogical descriptions for each rock. To make this raw database useful for field application, it pulls in external MinFile data and exact GIS spatial coordinates, routing every sample to a specific location in the real world. Text descriptions, however, lack the physical geometry required for true structural analysis. SEG partnered with the nonprofit group Below BC to generate high-definition digital twins of the physical specimens. They utilized 3D gigapixel imaging, a photogrammetry technique that stitches together hundreds of high-resolution photographs to capture the microscopic surface details, fractures, and textures of the rock. This interface demonstrates the result. At the top is a fully interactive 3D model, accompanied by a technical summary. Scrolling down reveals the specimen's collection details and a regional map pinning exactly where in British Columbia the rock was originally extracted. Layering rigorous metadata over a high-fidelity 3D image liberates the sample from the rock room, allowing geologists to conduct remote structural analysis from any location. Surface textures only tell half the story. To fully utilize these samples for education, the team needed to extract data about their internal alteration minerals. Originally, SEG planned to follow standard geological protocol, selecting 100 core samples and turning them into thin sections. A thin section requires a physical rock to be aggressively sliced and ground down to a translucent sliver, so light can pass through for analysis. The primary drawback with this method is that it permanently destroys the source material. For a curated legacy archive, sacrificing irreplaceable teaching specimens is a massive operational cost. Furthermore, preparing thin sections is incredibly time-consuming, and the resulting microscopic slides offer limited immediate utility to field prospectors who need rapid identification techniques. Recognizing these constraints, the team abandoned the thin section plan entirely and pivoted to a non-destructive testing methodology. Forcing themselves to prioritize the physical integrity of the legacy collection led them to a faster, scalable way to extract the necessary pedagogical data. The solution they deployed was a handheld diagnostic device called the ASD Terraspec Halo. The device operates on the principles of shortwave infrared, or SWI, spectroscopy. Instead of cutting the rock, the instrument bounces specific infrared wavelengths off the specimen, measuring absorption to generate a unique spectral signature. It instantly cross-references that signature against an onboard database to pinpoint the exact molecular composition. This image shows the scanner in action. The digital readout displays a precise match for alteration minerals, specifically identifying K-elite and kaolinite. Notice the physical rock specimen remains intact. The scanner rests against the surface, yielding highly accurate data without a single cut. This immediate identification of alteration minerals directly feeds into the curriculum for their Advanced Prospectors course, providing real-world diagnostic examples. By utilizing spectral analysis, SEG eliminated the preparation bottlenecks of thin sectioning, accelerating their data gathering while perfectly preserving the archive. With the samples digitized and their mineral compositions identified, the next step is to pull these isolated data points back into a macro-regional context. SEG applied this synthesized data to create a self-guided spatial mapping program, the Babine Lake Hazelton GeoTour. This webpage header outlines the GeoTour interface, designed specifically for geoscience professionals. It provides a structured guide to the regional geology, correlating directly with the physical trays of rock housed in the Smithers Archive. The curriculum focuses heavily on examining the older, underlying components of the Stikine terrain in west-central British Columbia. This bedrock map outlines the project's geographic scope. Dense clusters of red and blue pins represent locations where field data and digital samples are mapped. Using the right-side legend, users can filter layers to track regional structures like Jurassic, Cretaceous, and Eocene assemblages. Each of those pins links a specific field outcrop directly back to a 3D digital twin of a rock sample originally collected from that exact location. To provide comprehensive visual context, the tour utilizes GigaPan technology. These specific links for stops 28 through 33 open massive, ultra-high-resolution panoramic images of the actual field outcrops. The virtual GeoTour successfully bridges the gap between studying a macro-level regional map and conducting micro-level analysis on an individual stone. All of this database architecture culminates in SEG's primary educational output, an intensive, modular, advanced prospectors course. The course combines the spectral data, 3D imaging, and GIS mapping into cohesive, interactive digital modules designed to train industry professionals. This poster maps rock samples against regional metamorphic facies. The upper section visualizes temperature and pressure gradients deep underground. The lower bar shows structures deforming across the transition zone, moving sequentially from slate to phyllite to schist to gneiss alongside visual samples. This represents the complete data journey, from a physical rock to a 3D digital twin, to a precise data point, to a node on a map. Instead of relying on static, physical database entries logged on paper, the system operates as a synchronized digital geographic network. There is now a direct tether connecting the physical asset on the shelf to a globally accessible digital ecosystem. This powerful hybridization entirely resolves the geographic isolation that limits the utility of legacy collections around the world. The Smithers Exploration Group proves that physical geological archives do not have to be passive historical records. When rigorously digitized and mapped, they operate as dynamic, borderless engines for training the next generation of explorationists.